welcome to the plenary session today. We are very fortunate to have as our plenary speaker Professor Kannan Ramchandran from UC Berkeley. Kannan's work has of course inspired many of us over the years with his contributions to distributed source coding, network coding for distributed storage, and a number of other problems such as distributed computing or private information retrieval that are very well represented at this conference. For his work, he received many awards, including the Best Paper Awards from Communication and Information Theory Societies, as well as the very prestigious 2017 IEEE Kobayashi Award. So if you haven't had a chance to congratulate him yet, this is our chance to congratulate him again. So please join me in congratulating and welcoming our plenary speaker, Professor Kannan Ramchandran.
Thank you for the introduction, and thank you for the honor of speaking to you. The title of my talk is Codes for Speed, a Clear Advantage, Computing, Learning, Access, and Recovery. And keep expectations low. I want to start by saying don't expect too much, and you'll be fine. So, as always, we start with Shannon's legacy, this architectural block diagram that revolutionized information for source coding and channel coding. But this channel coding picture, you can, of course, compress the source at its entropy, and channel coding, there's a channel capacity, and you can transmit at rates up to capacity. And this has had a long-lasting impact on the community and on our industry. The form of both source coding and channel coding. So here are some source codes: Huffman, Tunstall, Arithmetic, and Lempel-Ziv. And channel coding with Hamming, Levine-Solomon, low density parity check, Turbo, and more recently Polynomial. And that's the QR code of my webpage, in case you're wondering what that is. Okay, so let's look at channel coding, and let's do a very short primer on error correcting codes. Given that we are in Vail, I thought we'll take the occasion to see what happens if you want to deliver 3 data chunks, x1, x2, and x3, and with 4 skiers, each carrying 1 chunk of data. So one skier can carry only 1 chunk of data. And you know one of them is going to get delayed, but you don't know which. And so what do? Well, you add a parity, right? That's your x4, x1 plus x2 plus x3. And sure enough, x2 gets clobbered by a tree, and you recover x2 by decoding it from the other guys. So this is the essence of error correction coding. And this also has the MDS property, the maximum distance separation property, which is, if one of them gets lost, you can recover from any 3 of them. Okay, error correction codes are used extensively in communications and storage in the form of low-density parity check codes, and Reed-Solomon codes. And here's a laundry list of all the applications where they have been used, from Wi-Fi to DVB to WiMAX, cloud storage, QR codes, and you name it. So this is all due to the impact of Shannon's architecture. Okay, so this is not what I'm going to be talking about. This talk is not about the classical applications of communications and storage. I'm going to try to steer the talk in an outward way, outward view for codes, in particular looking at big data, okay, which is kind of the modern age. And the clear advantage refers to computing, learning, access, and recovery. And we're going to look at how codes can be used to speed up each of these activities, from computing, learning, access to recovery. And that's my title, Codes for Speed. So the outline is going to be, I'm going to start with access, and then move on to recovery and learning, and then finally to computing. So I'm going to have a broad view of things. So it's going to move along, except for the middle part where I'm going to dwell a little bit on the details. Okay, so chapter 1 is speeding up data access in distributed storage systems. This is joint work with Alex, Rashmi, and Nihar. So the Hadoop distributed file system, which is running most of the data in the data centers today, consists of 3 copies of the same data. So you have, for example, a 640 megabyte file will be chunked up into 10 pieces, and each one will be 64 megs. And you'll have 3 copies of each. And this leads, obviously, to the big problem of thousands of nodes and multiple tens of petabytes and growing. And the storage efficiency is the main driver for cost. So you could obviously do this RAID, which is a 1410 code, which would be a Reed-Solomon code, where you would have 4 parity symbols for 10 of them. And this will obviously reduce your storage from by about 53%, from 3x to 1.4x. And this is obviously very useful for less frequently used data. So Reed-Solomon codes are obviously used. But the speed of access, especially in the event of unavailability, is not clear. So what do I mean by that? Well, codes are good, but the good news is we can now tolerate 4 node failures. Suppose the user wants 3. Let me see which is the... Yeah, so he wants 3. And in these distributed storage systems, the files are spread out over all the disks to the point where any particular user's data is only in one disk. So you really only want part of the data there, which is in number 3. So if the user wants 3, but the server is unavailable, then you want to free up another server, call it 3 prime, which will take the place of 3. And you read from any 10 nodes, and then you send all your data to 3 prime to repair the lost block. Because in order to repair any one of them, you have to get everybody, you get everything, and then you keep what you need. But that's kind of wasteful, because this is also called a degraded read, because when 3 is not available and a user asks for it, this is an alternate way for the user to get his data. This read is very slow, and the network traffic is high, and you're reading 10 times more than the lost information. So it's the best of both worlds possible. So can we have the storage efficiency of codes and the bandwidth efficiency of replication? Because when you replicate, you can get it immediately. Almost. There is an optimal trade-off. And these are regenerating codes that were done about 8 years ago. It's been a long time. So how do they work? Well, this is just an overview. On the y-axis is storage. On the x-axis is the repair bandwidth, or speed. And you can see that the Reed-Solomon codes are all the way at the end. Oops. Yeah, so Reed-Solomon codes are at the end, and the MSR and MBR are minimum storage and minimum bandwidth regimes, which are at the end points of the trade-off curve, though this is an optimal trade-off curve. And it's linearly, it's piecewise linear. And you can see that you can get substantial savings from this. Okay, I didn't know how to get this. Okay, so now, and lots of people have worked in this room on various points on this trade-off curve. This trade-off is achieved by doing an information flow graph over an appropriately chosen graph with sources and sinks, and finding the cut set bound and showing that you can achieve it with an actual code. Okay? So I won't go into the details of this, but this community has been extremely active in pursuing this direction, starting from regenerating codes to locally recoverable codes, to repairing Reed-Solomon codes and other variants, and codes with redundant request, which is kind of a confluence between queuing theory and coding theory. So it's kind of an interesting area. But that's kind of the overview. And the idea here is that all of these are trading off recovery time for storage cost in some meaningful way, and with the goal to improve the access of the recovery time. And in terms of impact, industry impact, piggyback codes and hitchhiker codes, these are variants of regeneration codes that Rashmi worked on. And these are in Facebook, in Apache Hadoop 3.0, NetApp, and Cisco. So this has made a huge success. More recently, there's been butterfly codes in Western Digital and Ye, Barg, and Clay codes in Ceph. So it's a huge success story in terms of what our community has done here. So that's kind of the takeaway from the access part of my talk. Okay. So let's pause and move on to chapter 2. So I'm going to dwell a little more in detail on chapter 2. This involves speeding up learning and recovery of sparse signals. So motivation, you have a data set, and you're given training points, x, y. Our goal is to learn a certain rule f that maps x to y. So x are the features, and y is the label, as we well know. And for example, x might be the area or bedrooms, and y might be the house prices. So they're obviously correlated. And questions of interest, what is my sample complexity? How many data points do I need? What is the computational cost? How much time does it take? And what is the robustness? So how accurate and stable is it? So these are all important questions of interest. And for example, if f is polynomial in x1 and x2, and you have only 3 parameters, so your problem dimension is 3, and it's somewhat easy because you can fit easily. But however, the reality is that n is something like this. It's some complicated thing, and you don't even know what it is, and you want to model this. And the problem dimension is getting large, and even if you have a polynomial time algorithm, that is kind of ramping up, and you feel frustrated. So can we do something about this? Well, what if you could cherry pick and actively choose training data? In some scenarios, this is feasible. And the model has sublinear degrees of freedom, meaning that the structure in the signal is only a sublinear in n is the dimension, in terms of the model. Can we then achieve fast and robust learning with active sampling and coding theory? So can we achieve the sublinear cost that we show here? Okay, so potential impact is huge because the applications of this are wide-ranging from MRI, magnetic resonance imaging, to radio astronomy, to sub-Nyquist sampling, to the Internet of Things, to computational imaging, to machine learning. So there are many, many apps for this. So I'll start by talking about the work we've done a few years ago on sparse spectrum, doing DFT as well as the WHT, which is the Walsh-Hadamard Transform. This is joint work with Samir, Simon, and Orhan. So let's start by doing a small exercise in polynomial learning. And this is something well known to all of us. So you're given a polynomial. You're given a polynomial, and you want to evaluate, you want to find the polynomial. You want to learn the coefficients of the polynomial. And if it's a second-degree polynomial, you can do it with 3 points. If it's a n-7th-degree polynomial, you can do it with 8 points. And an n-1th degree polynomial, so this would be your query. So you knock on the door with an xi, and out comes f of xi. So how many such xi's do you need? So it's very clear we need n plus 1, or n. So how do you solve for this? How do you recover the coefficients? Well, you just evaluate them at these xi's, and f of xi's are going to be popping out, and you get a van der Waals system of equations, which you can solve, and you learn the polynomial coefficients. So what points do I choose? Well,
I have many options, but if I happen to choose them equispaced on the unit circle, so the roots of unity, then you get the inverse discrete Fourier transform. This is the definition of the inverse DFT, or the DFT. So now comes the interesting part. What if I have only k degrees of freedom in my polynomial? So let's say that I have k, which is sublinear in n, which means that k and n both get large, but as a ratio, k over n goes to 0. That's what sublinear means. So then how many do I need? Well, example, suppose n is 1 million, and my sparsity is such that I have only 200 degrees of freedom. So ordinarily, I would have to do 1,000,001 points for this. So how many points do we need here? Well, spoiler alert, it's 616. Okay? I'll show you how that happens, but this is kind of at the core of what we're going to talk about. So the problem formulation is about computing the k-sparse discrete Fourier transform of x, and this is the Fourier transform. And we'll assume that the sparsity is uniformly random in the support. So here are the results. So this is called the fast Fourier aliasing-based sparse transform. So in the noiseless case, which means you're exactly k-sparse, you can compute k-sparse n-length DFT for a sublinear, where k is sublinear in n, using fewer than 4k samples. This is, I'm making things approximate here so that, this is a plenary talk, so I don't want to get into the details. But when k is n to the delta, where delta is my parameter, up to delta of 0.99 or something, 4k is sufficient, okay? And this can be done more surprisingly. Even now, it's surprising to me. You can do it in order k log k time. No dependency on n. And in the noisy case, there will be dependency, and there will be some log terms that pop up. I'm not going to talk in detail about this. But nonetheless, even if for noisy and noiseless, you see that I can do sublinear time recovery when the degrees of freedom is sublinear. So this is the message I wanted to give. And let's start by understanding why this may be true. I'll give you some intuition, hopefully. And the problem involves a puzzle of a gold thief. This is from the comics. And here's your sultan or king. He gives his 100-gram gold coins for safekeeping to his treasurers. So he gives them each. But there is one guy who's a thief, okay, among in the lot, and he steals an unknown amount, but fixed amount from each coin. Okay, so what is the minimum number of weighings needed for you to catch this guy? This is kind of well-known problem, and what do? So, well, you take the first coin from the first guy, and take one from each because you want to get a baseline. Since you don't know how much each one stole, the one guy who did steal. So you know that it was 100 grams. So in this case, if you had 5 of these, you would get, depending on what you do, you'll get a differential weight of -5. So for example, it would be like you had 495 grams when you took the 5. I'm just going to do it in differential form. What do you do on the next step? Well, you get 1 from 1, 2 from the second, 3 from the third, and so on. And if you do that, let's say you get -20 as the differential. What do? Well, you take the ratio of these, y1, y2, and form 4. And so number 4 is your thief. So what's important here is that 2 are enough, and every one of these columns is uniquely as a signature for who the thief might be. So this is the key property we need. So these columns are going to change depending on the application, but this concept is going to continue. Okay? So this is exactly the point. And the ratio test further identifies the location of the bad guy. Okay, so continuing, if you had 4 thieves among 12 treasurers, So now we open it up. What do? Well, you group them, randomly group the treasures. That's bin 1, there's bin 2, bin 3, bin 4. And you notice that the 4th bin has a multi-ton because you have 2 guys, and I was not equipped to deal with that. So, but this bin 3 is a singleton, so you can definitely solve for that. And if there is a single thief, you can do the ratio test as we did in the previous slide, and you can iterate. So you do that, and you nail down that guy, and that will immediately uncover the 4th bin, because there were 2 guys, and now he's uncovered, and bin 2, and so on. So you see how this goes. So the questions are, how many groups are needed? How to form the groups? How to identify if a group has a single thief? So if you answer these, you'll be answering all the questions that are coming forth. Okay, so let me switch gears and talk about the DFT problem, because this is just kind of a setup. What we're doing there is we're dealing with aliasing. So for those from Signal Processing 101, we know that a signal and its spectrum are represented. So if your signal has this spectrum, you know that if you sample it, you get all these copies. If you sample it fast enough, which is above the Nyquist rate. But if you subsample, you will get a picture like that, and you have no hope of recovery. Or maybe you do, if the spectrum is sparse. So that's what I want to talk about. Insights, so if you have subsampling below the Nyquist rate, then you have aliasing in the frequency domain. Now, if you have maybe a smart kind of way of subsampling for sparse spectra, then you might be able to generate a good, what I would call an alias code. So how do I find these? Well, these are going to be guided by the Chinese remainder theorem. And that will result in sparse graph codes. So we use coding theoretic tools to design and analyze these things. And the randomized constructions are used for design. And the density evolution, martingale, and expander graph theory are used for analysis. So we'll do a mean analysis, and then we'll make sure that it concentrates around the mean using martingales, and then show that the probability of error will go to 0. OK, now, what's the main idea? Let's do another example with n equal to 20. So this is a 20-point signal in time, and there's a 20-point signal in frequency. But only 5 of the 20 are non-zeros, as seen here. So if you subsample by 5, you get these 4 DFT coefficients, which are connected to the original 20 coefficients in a certain way. That's the aliasing. And that is exactly the 0 plus 4 plus 8 plus 12 plus 16 are the first one, and so on and so forth. So these are the groupings that we talked about in the thief problem that are going to be induced by subsampling. Okay? So you get these, and you notice that a lot of these lines are blank because they were sparse. And you want to exploit this. So what do? Well, the first guy had a 0. Nobody contributes to him. The second one had 3 people. The third one and the fourth one have singletons in this example. So you write it down, and you notice that I'm going to color code it, a red for multitons and a blue for singletons. What about, what's the next step we do? In the thief problem, we had this 1 plus 1, 2, 3, 4, 5, right? We got different weighings. How do we induce that in the subsampling world? Very simply, you just do a shift and subsample. When you shift and subsample, what happens is you exactly get the exact coefficients from the previous time, but they get weighted. And they each have a unique weight. And the weight is the phase shift because of subsampling. And you get exactly in this example, you'll get the 20 roots of unity, and you have W to the I for the ith guy that contribute. So armed with this, we're going from right to left. So you have x of n going in, you subsample, and you take a short DFT. This is where the complexity is coming in. You take the big DFT and make it into a short DFT. And here you subsample, and you get exactly what you had. And then you shift and subsample, and you will get the weighted versions of what you had. And so from now, you can see that I can decode. And not only, I can also subsample by more than one factor. So I can have perhaps subsampling by 4 on the next stage. And perhaps in a bigger problem, I might subsample by other factors. So what's the main idea? I'm equipped to deal with this problem because I have a peeling decoder, just like we had before. And you have the color identification of multi-tin and singleton. So we start. And we start peeling away, just as we did earlier. So once you're done, you see that sparse DFT computation is nothing but decoding over sparse graph codes. Here's an analogy. So on the right here, you have the non-zero DFT coefficients. And here are the aliased bins. So these are, if you will, the pruned graph after the DFTs, after you've had your DFTs. On the left, you have the erased symbols and packets. I'm trying to do the analogy to packet communications. So you see that on the left is an explicit graph, and the design is very well understood. On the right is an implicit graph, which is induced by subsampling. And you have n minus k correctly received words, n minus k 0 DFT coefficients. You have k erased packets, k non-zero DFTs. Here the peeling decoder recovers the values. Here the peeling decoder recovers both values and coefficients and locations. So this is the exact analogy at a high level between these two problems. So the sparse DFT computation is decoding over sparse graphs. Does it always work? No. Why would it work? You know, I cooked up an example to make it work. How do you make sure it always works? How do we induce good graphs that will guarantee that they will work? And also, the graphs have to be induced by subsampling. Well, I'll skip the details, but what happens is on the left here is your balls and bins model in sparse graph codes, where let's say you're throwing 2 left regular LDPCs, as they're called, and this describes the ensemble of all possible graphs on the left. On the right, it turns out that you need to have co-prime factors for these subsampling factors. When you do that, it turns out that, again, here you're subsampling by 4 and 5 in this example. So in this particular example, you see that 2 and 0 are mod 4. If you have the Chinese remainder theorem, if these are co-prime, you know the Chinese remainder theorem says there's only one number between 0 and 19 that uniquely represents these modulos, and that will be 10. And more generally, you'll have these labels that you can uniquely ascribe to each of these balls, which there will be a one-to-one correspondence between the balls and bins on the left and the Chinese remainder theorem on the right, this subsampling. So you see that there's an isomorphism between these two, and now you can dip into the literature of the LDPC codes and do your usual analysis of density evolution, martingale, and expander graph theory with a few twists. And just like as in LDPCs, you have a sharp threshold for where the channel, where the rates are going to be above channel capacity. You have a sharp threshold here where recovery is possible, and below that recovery is not possible. So as an example, to go back to our example I did with the 1 million and 200, I said I will let you know how I get this. This is the architecture for this particular object. So you it turns out it's not quite a million, it's almost a million. And you notice 100, 103, and 107 are co-prime. This is key. And let's say k was about 200, and we said m would be about 600. So we subsample by 100 by 103. And in fact, by all combinations of these, you have 3 stages. And notice that the main complexity here is in this DFTs. So this is order k. And so that's k log k, and that's where the complexity of this becomes. And back to the sparse polynomials, you see that if you do some bookkeeping and count how much data you have there, it'll be exactly 616. So this is the uncovering the puzzle that we had. Okay, what about for noisy signals? This is all well and good. How do I deal with noise? Well, it turns out that you can easily generalize the noisy to noise, noiseless to noisy, by simply repeating the number of shifts that you do in every stage. So instead of having only one, you would have order log n now. So I won't go into the details, but you can use this to basically overcome. So you need to have all these to do noise averaging in each stage so that you can be sure that that was the right guy. Okay, so what is the application? Well, there's an application in MRI for sparse DFT. So let's say that in MRI, you get your images in the K-space. So you take acquisition in the K-space, which is the Fourier space, and you have to take the inverse Fourier transform in order to get the image. So this is the MR images that you see. So, so if you can speed up the acquisition of the MRIs, then you will win, because the acquisition time is the key to speeding up MRI, and MRIs are very costly. So the hope is that you can run this, and here is an application to a numerical phantoms for cardiovascular MR done by ETH. And this is just a beating heart, and this is a 2D version of the problem that I talked about earlier. And these are the dimensions. So you exploit the fact that the temporal differences are sparse. Okay? So you see that this is the temporal differences in your image. And so the hope is you can exploit that. So we wrote a real-time reconstruction in MATLAB on a MacBook just to show you that, and this is taking about 33% of the Nyquist rate. And you can see the samples are very regular because this is uniform sampling, but many stages of it. And this is the recovery in real time. This is actually running in real time on MATLAB. So that's the end of the story on this. But you can see that this has many other applications. So anybody care to guess what this is? This is the first digital camera, believe it or not. This was done by Kodak in 1975. And Kodak is no more, so it's a pity. But they used to view the photograph by hooking it up to a television, and that's how you would see your photos then. So, well, this is not quite the most modern camera, but in Canon in 2000, you get a digital camera like this. So this obviously, I would argue that the digital camera came about, the main reason it came about was because of the viewfinder that you see in the camera, from which you can actually see the picture that you're trying to take. So guided by this, we can dream of a real-time MRI with a viewfinder. And this is something that one could possibly pursue. I'm not doing it yet, but potentially you can imagine that you could do the MRI in real time so that you can actually see what you're taking and adjust accordingly. So this is kind of one of the applications. Okay, another thing is that we have fabricated this in a hardware, in BWRC, and this is you can see here's the title, it's an ESSIRC. I don't even know what it stands for, but you can see that it replicates the architecture of what we did. And this is for, I think, 175 kilohertz resolution in about 1.89 gigahertz, about 2 gigahertz. It's doing real-time sampling, and this is used for heavy hitters in IoT and spectrum sensing, so you want to know very quickly where the heavy occupiers of the spectrum are. And you can see that it has less than 20 microseconds of acquisition time, so you can do it in real time. So this is another application. Okay, so let me change gears and talk about a cousin of the DFT, which is the WHT. This will be the Boolean version of what we talked about, and this is the definition of the DFT. And the endpoint WHT is given by this formula, where n is 2 to the little n. And here you can see that instead of taking an endpoint DFT as in the DFT case, you are taking 2-point DFT in multidimensional. setting. So it's a multi-dimensional DFT, but in each dimension you have only 2 points, and that's the Walsh-Hadamard transform. So this is useful in many machine learning applications like decision trees and regression trees, digital logic, evolutionary biology, fitness landscape comes into play, and hypergraphs. So the Walsh-Hadamard transform, this is just to visualize the fact that it's just the equivalent of the high-dimensional DFT over the hypercube. So if you have this 8-point signal, you would just fold it into a cube, and you take the 2-point DFT in each. Okay? That's what the WHT gives you, as you can see here. Now, the time domain and frequency domain views are such that if I were to take these 2 samples, C0 and C1, in the Walsh domain, you would be aliasing the frequency components that abut it. This is kind of like the projection slice theorem, for those who are familiar with that. So if you take, on the other hand, these 2, C0 and C2, then your aliasing pattern will be looking as shown here. And finally, if you do that, you get that. So this is just to show you that there is a similar correspondence between subsampling and aliasing, even in the WHT space. How does it correspond to polynomials and multinomials? Well, just like we had evaluations of the polynomials at the n roots of unity, now you do 2 roots of unity, which is 1 and minus 1. And if you plug that in, you'll see that you're essentially getting a polynomial, multinomial in x1 and x2 for the simple example of a 2-point signal. And you see that the sparse version would be where most of these coefficients are non-zero. Are 0. So this would be the sublinear aspect of the problem. So you can see here that this would, in general, be capturing the dependencies or couplings of the variables that account for the rule, for the f. And when you and all the non-zeros correspond to the kind of irrelevant variables that do not contribute to the eventual function. Okay? So this is going to be the key for us as we look at an example which we'll call the hypergraph sketching. So let's not worry about hypergraphs, just imagine it's a graph. And let's say, take an example of Amazon selling books. And S is the number of sales patterns. For example, X1 and X2 are bought together, and X22 and 23 are bought together, and 9 and 14 are bought together, and so on. And as you know, frequently bought books are prioritized by Amazon so that they can ping you with annoying ads on what to purchase, right? So now, how do we solve this from a sparse WHT viewpoint? Well, there is a very simple. Okay, first is if you allow for all possible hypergraphs, it turns out even for small, modest size like n equal to 30, you have 10 to the 9 possible hypergraphs. That's way too many. So you don't want to log all of those. So can I log only the patterns that matter, which is you observe that only a few purchases are made and only a few things go together. And if you sketch the cuts of the graph, what's the cut of the graph? Well, imagine that line there on red. You take everybody above the line to be +1, everybody below to be -1. And your cut value will be 0, right? Because nobody is cutting that. And if you move the line down, well, the cut value is 1, because you have exactly one guy cutting through that. So you have cut value is 1. And finally, you can do it for all other cuts. Notice that now you can write down this cut function more generally. And if you notice, these coefficients are corresponding that we have correspond only to the pairs x1, x2, x9, x14, and so on that are edges in the graph. So let's deal with edges. Only the edges appear as coefficients, which are non-zero weights. And all the others, all the irrelevant ones, vanish. So you don't have anything else. So can I possibly recover this graph by doing subsampling in the cut domain. So this is the idea. So small, and assuming that the number of sales patterns is small and the number of items per sale is small, you can show that k is less than s times 2 to the d minus 1. You subsample the cuts instead of having every one of them. And this will recover the edges. Okay? So here's an example with 50 books and 2 items per sale. This is supposed to be a sparse graph. It doesn't look sparse, but it actually is. And you have 250 sales patterns here. And if you were to look at the sparsity, it's less than 500. And it turns out you can do this with about 25,000 queries instead of 2 to the 50, which is impossible to do. And here are some of the, so for example, here's a cut you might do. In general, you would need to do every possible cut. But because of sparsity, you only take a few. And this is after a few iterations of my peeling decoder, and you are done. So moving outward, the source implementation, the open source implementations of these are in C++, publicly available on GitHub. So please check these out and maybe contribute to it or improve it. So broad scope of applications-wise, I have sparse spectrum. Here's the sparse graph codes. Now, it turns out that what I talked about, the general philosophy, the architecture of what I'm doing, can be applied to many other problems, including the fast neighbor discovery for IoT, which is used for group testing. And this is a very nonlinear problem because group testing is an OR function, which doesn't, codes don't go through. So you have to be a little careful about that. Sub-Nyquist sampling theory, which is kind of a, it merges sampling theory and coding theory in a beautiful way. Compressed sensing, where again, sublinear degrees of freedom will give you sublinear recovery time. So this is an important attribute. Sparse mixed linear regression and compressive phase retrieval, which are all going to have the same application space as we talked earlier. So it's like you sprinkle this magic dust and out pops all these applications. And in particular, you can see that the key here is that you have a peeling-based turbo engine, which has to be, it's kind of like Santa and his elves. Okay? So these are the elves on the side, which are kind of concurring or not concurring. And the problem is a divide and concur thing. And they will solve if trivial. They'll first guess that it is trivial, and they'll try to solve it. If not, they'll say, I don't know how to do this. If they can do it, they bring it back to the main engine, and then and that will peel off more people, and then they'll keep going that way. So this is the turbo engine that works, but the solve, this part has to be done. I'm going way far ahead. Hang on a second. Yeah, so the key is that the problem-specific subcodes have to be designed for these. And this is where the creativity has to come in. Okay, and I've given some examples of some of the tests that you would do in the sort of the small validation box that's going to sprinkle the engine. Okay, so moving on, speeding up distributed computing on the cloud is going to be my last chapter, which is going to be a little short one because I'm running out of time. And this is joint work with a whole bunch of people, Kangwook, Ramtin, Dimitris, Orhan, Vipul, and Tavor. Okay, so we are in the throes of a new kind of noise with this big data systems. And these are identified by hardware failures and maintenance and network bottlenecks. So latency is showing up as system noise. And you can see that sometimes we get to complete it fast, and other times it's completing and still doing its thing. So the straggler problem is well known, but this was actually started, was brought to our attention in 2013 by Jeff Dean at Google, who said that the scale and the complexity of the modern web services make it infeasible to eliminate all latency variability. So you might as well take it for granted that this is going to be there and deal with it. And here are some examples of the kind of numbers that you see for 95th percentile and 100th percentiles, you can see the gap from 95 to 100 is quite large. This is where all the straggling is happening. Okay, so how do we deal with this? So let's take the case of a distributed matrix vector multiplication. I'll stick to matrix multiplication for this talk. And let's multiply A by B, where you have a master node and you have a bunch of workers who are going to do part of their work for them. So this is the massive distributed computing era that we are in. So more generally, this will be thousands of machines, but let's think about 3. So if you have A1, A2, and A3 as the 3 components of A, you split A into these 3, and you can have each of them do a little piece of the puzzle, and then you kind of aggregate the results. So that's easy enough to do. So worker 1 does A1B, worker 2 does A2B, and worker 3 does A3B. And there comes Y1, here comes Y3, and there comes Y2. That guy is straggling. Okay, so that's the slow guy, and you want to deal with it. So the question is, can we use codes to provide the distributed algorithms, to provide the algorithms with the robustness you need against these stragglers? So this is the theme of this part. And what would you do in the coded matrix vector multiplication case? You still get only 3 servers, just like in the previous case, just for fair comparison. So now you chunk up A into 2 parts instead of 3 parts, A1 prime and A2 prime, and have the 2 guys do A1 prime B and A2 prime B. And you have the third one do the parity. So this is over the reals. So it's not over a quantized field. So he does Y3 prime plus Y1 prime plus Y2 prime. So that's what we do here. And that's the straggler. Y1 prime comes, Y3 prime comes. And note that I have accounted for the extra computing that these workers are doing because the size of A1 prime is now larger than that of A1 earlier. And you get Y2 prime by just decoding. Okay, so how does this work? Well, under an exponential latency model for the recovery time, for the service time, you can show that in theory there's a log n gain in between doing optimal replication and optimal MDS. And this is pretty much mirrored in the Amazon AWS, the plots that we ran for empirical validation. Okay, so this is pretty standard. And this was documented in these works. Many, many applications. I won't even begin to enlist them here, other than to give a list. There is, because we are in the machine learning age, so distributed learning or logistic regression, distributed nonlinear function computation, and reducing communication and data shuffling by network coding, where you can explore the trade-offs between communication and computing, has attracted lots of interest. Coded matrix multiplication, distributed gradient coding, and also you can argue that I don't need the exact answer. What if you only want an approximate answer? Because that's what SGD does, stochastic gradient descent. And there are many variants of this. There is an SVD decomposition with sequential coding and sketching and second-order methods, coded control, you name it. I think this is an exploding area, and I think the community is getting charged up with this. But I would start with a particular take on this that I'm particularly interested in, which is computing on the cloud with something called Pyren. This is an AWS Lambda system. So this is work done by my colleagues at Berkeley, Eric Jonas and Ben Recht and so on, who are the title of his paper is Occupy the Cloud and Distributed Computing for the 99th Percentile. So the cloud computing is reserved for the very elite. We need to know exactly what we're doing. It's too damn hard. So can we make this happen for you and me, for the regular Joe? So this was the goal of this. And it turns out that Amazon released this particular microservice platform called the AWS Lambda, which gives you a single core and tons of RAM, 1.5 gigabytes of RAM. And it gives you a runtime of 300 seconds max. and you can run it on Python or Java. So here's your laptop, and here's the cloud. How does this work? So what these guys did is that they said, if you can handle small jobs well, I'll take a big job and split it into these small little jobs, and then I will deal with the big jobs. So it's a clever way in which to kind of fool Amazon into thinking they're doing small jobs when you're actually doing a big job. So this is the idea. So you write a function, and you upload the function and data to S3. And then you invoke the Lambda machines. So you have to write the function and the data to S3, which is the storage unit of Lambda, of Amazon. And that's a very fast interface between the storage and the Lambdas. So these Lambdas just come up, they have some code, they just run the code, and then they go away. And they don't even know what exists. So it's serverless, okay? And this is how you invoke the Lambda machines. And finally, you have to poll the S3 for the results. And when you're happy, you're done. So this is the new paradigm. And if you look at what's going on here, this is a channel plot, if you will, of this AWS Lambda system, which is very complicated. I won't go into the details. But you can see here that this is the sequence of things that you do from the time you start, you submit, setup done, and the results are returned. But the key thing here is that you have 400 stragglers out of 6,000. So now, the other thing is that the Pyren can handle up to 16,000 workers. So this is the kind of scale that we're dreaming about for making codes happen. So even on on a 6,000 node machine, you have about 400 stragglers. So scalable computable coded computing, note that latency is the sum of encoding time plus computation time plus decoding time, plus communication costs for moving data in and out of these distributed systems. So if you look at MDS codes for matrix vector or matrix matrix that have been studied, they only target for one of these three components, which is the compute time, but not for the encoding and decoding, which can be really, really large in a large-scale platform, especially when you have no servers. Okay? So at scale, what do you do? Can you do decoding on the fly? Do codes still exist? And you have to deal with real-valued computations. So there's a line of work that we have introduced called product codes that offer a good trade-off between being near MDS and having very local encoding and decoding. And if you come to the session today at 3:20, I believe, it's a straggler session. I think there will be a talk on this. Okay, so just as a startup, as a kind of getting warmed up, we just tried to do this for finding the principal eigenvector, which is used for PageRank. You want to find who's the heavy hitter. So I want just the one component. So this is a 10K by 10K matrix with 121 workers. We are just warming up here. And we found that there's a 33% savings. So basically, you saw that we got a 33% speed up in that system. So just to conclude, I've taken you through a broad survey of many things that codes can bring to you in computation, learning, access, and recovery. We looked at access, regenerating codes, and beyond. Learning and recovery, we used sparse graph codes-based peeling core with a verification test that was problem-dependent. And in computation, which is still an ongoing area, straggler proofing, large-scale distributed computing. So let me thank you for listening to me and conclude on that.
Thank you for a beautiful talk. So I was curious for the Pyren application you mentioned. What type of computations are they looking at?
Oh, you can do anything you want, but here we were looking at matrix multiplication. But because the matrix multiplication is kind of the core of many, many machine learning problems. So we just took that. But they were generally using it for, you can do anything you want. As I said, it's completely, it doesn't know what it's doing. It just goes and it gets the data, it does it, and goes away. And then it does it for 300 seconds. So you have a 300-second window over which to do the job. So that's why you can run big jobs. If you can do it in less than 5 minutes, this is a great platform.
Okay, thank you.
Again, thank you for a very beautiful talk. Two questions. One, you mentioned sensitivity to noise only when you talked about DFT in the beginning, but then you didn't mention only erasure in some sense, but you didn't mention noise, so I wonder if there is anything about that. And also about lower bounds, so are we in the limit? These methods you presented are the best possible? Is there a known bound for what is best possible?
Yeah, okay, so with regard to the first question, I didn't touch at all on the noisy part because it gets a little involved, but generally all the results follow through for the noisy case, for all the things that we looked at. So you will have, obviously you will have a hit due to the noise, but you will remain sublinear. You will only have log factors, not linear factors. And with regard to the second problem, what did you ask again? I forgot.
It was about lower bounds.
Lower bounds. So in some cases we do. For example, in the case where we did compressive phase retrieval, it turns out that you can at least come very, very close to the lower bound in terms of the number of measurements for the noiseless case.
Just to follow up on the previous question, we know that the verification-based algorithms are quite sensitive to noise. And I was wondering what techniques you use in order to deal with noise in verification-based decoding algorithms on sparse graphs.
Yeah, so the algorithms we use are simply to noise average out the verification tests that you're doing. So you want to make really sure that the verification that you did was accurate. And they are sensitive to noise, but not overly sensitive. So I would argue that at some reasonably high SNRs, they will work, but at very low SNRs, they won't work. And you would have to do other techniques like convex optimization and other things.
Okay, thank you.
Okay, maybe we have time for one last question.
Speaking about the code for computing, you consider the case where you have essentially an erasure probability, some erasure of some of the workers are struggling. Mm-hmm. Now, a more common situation is where you have clusters of data, of servers that are more reliable, and then you have maybe many of them. So you have like an unequal situation. There are chances of, the chance that the server will fall depend on the architecture. So the question is, can this be extended to like unequal protection that is tailored to the specific architecture of, let's say, the cloud or the environment that you are working at?
I'm sure it can be.
Like unequal protection.
Yeah. I think just based on what you're telling me, it seems like it can be done. I haven't done it, okay. And I don't think people, maybe it'll be the next topic people pick up.
Okay.
There has been some work done. Okay, good. Ramtin says, sure enough. It's a fast-moving area.
All right, I'm sure there are more questions, but let's wrap up the plenary session now and thank once again Kannan for a very wonderful.
Thank you.